Hello and welcome to my presentation on my project building flexible biological particle detection algorithms for traditional and emerging real-time instrumentation in collaboration with droplet measurement technologies. So let's talk slightly about primary biological aerosol particles. What are these and what do they do? So these can include all sorts of organic materials such as pollen, bacteria, viruses, and they contribute to several important atmospheric processes including cloud condensation nuclei, ice nuclei, and gas particle partitioning, forming both volatile and non-volatile secondary organic aerosols. They also play a large role in public health and agriculture, with the transmission of pathogens such as influenza and the currently topical coronavirus, of course. Therefore, then, being able to detect these and analyse them in real time could represent a significant step in developing early warning systems for both public health and national defence, as well as helping further our understanding of how these aerosol particles interact with their surroundings and the environment. Of course, being in collaboration with droplet measurement technologies, I shall be implementing their patented WIBS Neo. So what is the WIBS Neo? Well, the WIBS Neo is the wideband integrated bioaerosol sensor, and it utilises a form of ultraviolet light-induced fluorescence technology, which isolates distinct fluorescent signatures emitted from the aerosol particles. How does it do this? Well, the aerosol particles will flow into the instrument through an inlet, as shown in the diagram, where they are excited by a diode laser and two xenon flash lamps, 280 and 370 nanometers. Upon excitation, these fluorescent signatures are emitted from the particles and detected using two emission bands. And these bands correspond to common proteins and fluorophores, including tryptophan and NADH. Additionally, particle size and asymmetry factor can be achieved using a multi-element forward scattering detector, which is built into the instrument. So now we know a little bit about the WIBS Neo, how do we propose to tackle this project? What's our research strategy? Well, firstly, we'll need to develop a working knowledge of the WIBS Neo and dedicated analytical software. We'll need to examine and evaluate current detection algorithms used. We'll also need to identify the limitations in these current algorithms and develop a plan to improve the classification capabilities of the UV-Liv instrumentation. And then finally, to develop strategies for mapping information from high resolution to low resolution instruments to build more robust detection networks that don't cost a fortune and aren't really expensive in both terms of the skill set needed and the training needed. Lastly, then, let's talk a little bit about the machine learning. So what is machine learning? Well, it's often described as an adaptive ability of a system to perform the same task or tasks with increased efficiency or accuracy after each run. And it's achieved this using complex algorithms which are either trained, also known as supervised, or untrained, which are known as unsupervised. In particular, scikit-learn offers a variety of industry standard algorithms, both unsupervised and supervised, two of which I have listed below for your attention. With that, that concludes my presentation and my PowerPoint. Thank you for taking the time to have a look at this poster, and if you have any questions, please don't hesitate to get in touch. Thank you.